We started looking at this at the end of a recent class. We're often faced, especially in social and behavioral sciences, with outcomes, response variables that can be encoded as 0 and 1, 1 if an event happens or if a characteristic is present, 0 if not. And so just as a selection, I mentioned these the other day. Probability of voting for a particular candidate, like the candidate for president of Peru, Fujimori, based on some other predictors, probably nation goes to war given information, probability of loss of a AAA bond rating within some period of time, given economic information about the country, and this probability about that a respondent has some information, some knowledge that we can check, such as the example that we're going to see in a moment. Probably the person knows who Nancy Pelosi is, can identify her as the Speaker of the US House of Representatives as a function of how often they read the newspaper or some other information that we might want to understand the connection. But this is the one that we'll be using as an example. So same motivation as ordinary regression, but the dependent variable has to take 0 or 1 only. When we talked about you actually can just use ordinary regression, you really have to take it with a major grain of salt. Of course, the relationship is highly nonlinear. The errors or the residuals are very weird and patterned because the observations are going to always be 0s and 1s. And so, subtracting those, minus the predicted, the probability, you're going to get highly non-normal clustered errors. And but as a quick glance, to the extent that it is useful as a rough description, you can still do it. It'll work. Obviously, particularly bad for prediction, as we said, because you're gonna, for certain values of the predictive variables, you're gonna have probabilities predicted that are negative or more than 1, and so it's not useful to make those predictions that have to be wrong. But essentially, what we're just think about what we're trying to do in using those 0s and 1s to estimate conditional probabilities is sort of a, we think about again, what's going to happen here is that we've got a bunch of data points that are all going to be on the essentially on the 0 or on the 1. So if this is 1, and I'm actually gonna say it's such a bad, well, okay, fine, here's 0. Poor line there. But essentially you've got a bunch of, if this is the single predictor, and we can of course have more, here's X for different values of X. Well, you're only going to get one of 2 values for Y on the vertical, or right? And essentially what we're trying to do is, you can think about it that if we had lots and lots of data, right, and we were trying to condition, essentially you could think about this as an estimate of, in trying to relate X to a probability. Remember, probability here is just as in regular ordinary least squares regression, it's still expected value. It's still a probability in this case is, what's the for a particular value of X, what is the expected, what is the expected value of Y, right? What is the expected value? That's a very bright green. What's the expected value of Y given a specific X? Right? So it's really the setup, even though we're talking about probabilities now, even though we only get to see 0s and 1s, is really quite similar to the setup for ordinary least squares regression. It's just that our estimates of how good or how bad the notion of minimizing errors is a little funkier, right? But you could think about, like, if you had enough observations saying, okay, well, what's for an X here, what's the expected value of Y? What's the mean of my ones and zeros? And that's going to work out to a proportion, which would, say, all right, like if there's, say, 40 here and 10 here, we might say, right, 10 divided by 50, it's about 20%, right? But we don't get enough of these data points, right? So we've got this kind of moving average conditional on X. And, one way, of course, again, to think about that is just to think about a sort of a line. Oops. Yeah, that's awesome. But, then you get this problem of predictions that are way off. And so much better in terms of a kind of shape of the function would be to, if the probability is increasing, it's got to be limited at 0. So having it sort of curve up and then level out so that it's never greater than 1 or less than 0. And if it was decreasing, if as X increases, the probability of Y equaling 1 decreases, then it should, look something like that. That's one option. Of course, if it's not so steady, then maybe it would be like a step function that's kind of decreasing like that. So for various reasons, it makes sense to rethink how we're modeling the outcome as a function of the inputs. And how can we do that here? Well, in general, the way that we can think about generalizing a notion of linear regression, not just with 0 and 1s, but with a lot of other situations where ordinary least squares doesn't work, is that instead of modeling the mean of Y with a linear combination of predictors, we can model some general function of it, right? So instead of simply looking at that regression line, which is a linear, it's a line representing a changing expected value or mean, we can have some transformation of that Y bar. So how is that different from what we just did last week, or I guess the week before, on transformations of dependent variable? Well, in this case, we're not actually transforming the the dependent variable per se. We're actually just transforming the average, right? We're not going to take those zeros and ones and actually turn them into something else by taking a logarithm or taking a square root or squaring or anything. All we're doing, right, is thinking about the prediction as a mean, and not directly predicting the mean, but doing something to that mean to transform it. We're not doing anything to the individual Y's, the 0 and 1s, just to the averages. Okay, so as I mentioned, one problem we want to get around is we don't want predictions to be greater than 1 or less than 0. So we'll take this example of, we'll call knows Pelosi is the dependent variable. It can be 1 if the respondent knows and correctly identify who Nancy Pelosi is, 0 otherwise. And we have this long named variable, days reading newspaper, which can be anywhere from 0 to 7, self-assessed number of days reading a newspaper. This data was collected some time ago, although not so long ago that we shouldn't have. Oh, and I think that there were other variables that were involved, like reading news online. So we might not expect that days reading newspaper would be a very good predictor if many people aren't reading newspaper anymore, but still get information about politics in other ways, unless they understood this to mean also websites for newspapers. So which can predict probability of knowing to be Yeah, well, oh yeah, I was just giving an example. Like if we just directly model this probability, that is as like it's really like a y bar in OLS. So it would be like taking averages, ones and zeros. It's possible to have a weird probability. Instead, we're going to do something, the transformation that we're going to do, the function of y bar that we're going to take is going to be log odds, and that's going to involve a function of expected value. Okay, so we need to just take a step back and have a little refresher. Often we use odds and probability in everyday language as if they were interchangeable, but their technical meanings are different, although tightly related. So think about what odds are and how they're really a transformation of probabilities themselves into different scale. So odds are defined as a probability divided by 1 minus the probability. So if we're thinking about X as being an occurrence of some event or some characteristic, rather than a more general random variable, this would be, maybe I should say, probability of event E instead of X. Probability of occurrence divided by the probability of non-occurrence, right? 1 minus the probability of occurrence is the probability of it not occurring or not being present. So the probability of rolling a 5 or a 6 on a 6-sided die that's fair would be 1/3, 0.3333, continuing. So what are the odds? Well, just using the definition above, it's going to be 1/3 divided by 2/3. The thirds, the two denominators cancel out to 1/2. Often that's written or spoken of in everyday language as 1 to 2 odds, right? For every 1 chance at getting a hit, you have 2 chances of not getting a hit, right? So there's really a different, unlike probability, which has a denominator of the total things that can happen. This is really splitting it up as the total, we'll call these, successes in this example, ways of getting success divided by ways of getting failure, essentially. So probabilities have to be between 0 and 1, but odds can be any positive number. So that by switching to odds from probabilities, we're already avoiding one issue. We're not going to worry about getting nonsensical odds, nonsensical probabilities that are bigger than 1. We're going to have odds that are trapped between, are bigger than 0, and anything bigger than 0 for odds is acceptable. But we still get negative predictions, and we don't want that. So we're going to transform these odds further by taking a log. You'll see in a moment. So first examples, suppose that if you get at least a G, a grade on your homework grade, and oh no, I see. Let's say the next homework, the probability of getting at least a G on the next homework, given that you understand, let's say this video, is 0.99. So what are the odds? Odds are probability of success divided by probability of non-success, right? So 0.99 over 1 minus 0.99. Odds are 99 or 99 to 1. Strictly speaking, you can just say odds are 99, but we usually, as a reminder of this kind of invisible denominator, we would say 99 to 1. And you could also say 198 to 2. So let's actually think about how we move from a probability scale to a odds scale. And then we're going to also move from probability to odds to taking the log of odds. And the idea is that, you don't usually call it LO, but I'm doing it here for log odds. The idea is that, probability are all squished up between 0 and 1 with a kind of important marker of 0.5, which separates the higher probability of loss than gain, let's say. When we move to odds, everything in there from 0 to 1 is going to be transformed into being on the positive real line. And in fact, I guess if I want to keep the same scaling here, which is going to be risky, it's not going to give me a lot of room to work with, but I'll just point out that anything in the 0 to a half or 0 to 0.5 range in probability is going to result in odds that are between 0 and 1, right? So for example, a quarter probability or 0.25 probability, that's going to be 1/4 over 3/4 is going to wind up being 1/3, right? And so let me change the color of my, it's not letting me find it. Here we go. Pen color, let's do red. So here is 0.25 or 1/4 is going to get sent to, I probably made it a little bit too, probably should be probably around here, 1/3. Even that's probably a little bit, that doesn't look quite right. Oh yeah, no, that's fine, right? Because here's 0.5. Yeah, sorry. Okay, and what about 0.5 itself? 1/2 divided by 1/2, right? 0.5 probability of, we'll just say probability of knowing who Nancy Pelosi is divided by probability of not knowing. If it's 0.5 in probability, that's going to go to 1 in odds, 1-to-1 odds, right? If you had something like 0.4, right, which is 4/10 divided by 6/10, right? 0.4 is that right? 0.4, yep. Let's imagine we've got a 0.4 in there. Right? 4/10, sorry, divided by 4/10 divided by, I might have said it wrong, divided by 6/10. My probability of not is 4/6, they're 2/3. Right? So from 1/3 to 2/3, sorry, from 0.4 odds is going to be 0.4 divided by 0.6. That's 4/6, they're 2/3. Main thing I want you to just see, the key piece here is that numbers that are in this range, just between 0 and 0.5, are going to be spread out between 0 and 1. And then numbers like, for example, what happens with 0.75 or 3/4, 0.75 divided by 0.25. I'm going to have to send it way off. Right? 3/4 divided by 1/4 is going to be 3-to-1 odds. So really, I need to send that way out. We've got 1, we've got 2, we've got 3 off, way off to the right. Right? If we've got, let's say, 2/3 here, or 0.67, 2/3 divided by 1/3, odds will be 2-to-1 odds. Okay, that one is going to go here. But notice that as we get closer to 1, let's say like the example we saw, 0.99 odds will go way out to 99, right? 0.99 probability rather will be 99 divided by 1, 99-to-1 odds. Okay, what we want to do though is, again, this kind of makes things really asymmetrical, and still, if we just predict odds directly from a linear combination of x's, we could still get negative predictions, which won't make sense for odds. And then we have this other issue that, all of the poor chances of something happening, right? So between 0 and 0.5 is going to get transformed to being somewhere between 0 and 1, and everything between 0.5 and 1 is going to gets lots of breathing room. It could be out by 1 to infinity, right? So what we're going to do is I'm going to change the scale a little bit to fit this on here, and I won't belabor this too long. We'll talk more about this probably again in person, but if odds are stuck between on the positive numbers, well, and notice that let's actually see, probability of 0. 1 would go out to infinity, 1 divided by 0, but probability of 0, 0 divided by 1 is still going to be 0. So probability of 0 is odds of 0 as well. But when we take and actually we're going to take the log of odds. We're going to want to do, we're never going to actually be able to take exactly, well, fortunately, this isn't really uncertainty when something is 0. We can't actually take the log of 0, but we can take logs of very small numbers. And basically, let's think about, as before, let's think about sort of a important separating is the 0.5 probability or the 1-to-1 odds. And we're going to be back to, maybe I'll keep 0 here. Yeah, let's do it here. So this is nice symmetry. Okay. Log odds. Well, what does, if we're taking the log of something, log of odds, remember odds is a probability of something divided by 1 minus the probability of that occurrence or condition. And remember, log is of something is the power you would need to take the number e, 2.72, to get that. And so log, if we say that, what is it? The log of what is going to be equal to 0? Well, right, what's the e to the 0 is 1. So odds would have to be 1, right? So probability 0.5 log, sorry, to odds is 1, to log odds is 0. So the sort of dividing line between more likely than not and less likely than not. Oops, I wonder if I could do that. That was unfortunate. Did not mean to, let's erase that better. And what we have, that dividing line is 0.5 in probability, 1-to-1 in odds, or 1 and 0 in log odds. That's great. And we can think about, probably be a little bit easier to think about if we were doing log base 2 or log base 10, but the norm, for reasons we've encountered before, is to use log base e, or 2.7. One thing I'll actually just leave it here for now, we won't go any further on this because I want to move on, is that generally speaking, as with a normal logistic curve, is going to mostly get results that are between -3 and +3. And you can, I'll leave it to you to figure out what probabilities, right? You could try this with different probabilities. Try 0.8 divided by 0.2, you get 0.4. Take the log of 0.4 and see what you get. See what it takes for a probability to have a log that's equal to something greater than 3. So the main thing I want you to see now is that, the low probability events between, the less likely to happen than not happen, between 0 and 0.5 probability, between 0 and 1 odds, they're going to be going to negative log odds. Right? It's going to go somewhere down there. More likely than not kinds of events have probabilities between 0.5 and 1, odds between 1 and infinity, and log odds that are positive. Okay, so this is going to give us back a sort of symmetry. Log odds that are a certain amount negative versus log odds that are a certain amount positive will have a nice symmetry to them. Okay, log odds is just another word for logit, and that's what we're going to build our model around. And so the transformation in this generalized linear model is we're taking our 0s and 1s, we're predicting not just the average of the 0s and 1s, which would be a probability, but we're taking the probability for divided by probability against and taking the log of it. Okay, and so we want to model that as a linear combination, or just intercept plus slope times the predictor of interest. So log of the probability that the person knows Pelosi divided by a probability doesn't know Pelosi. We're going to model that. And for change, because I want you to get used to, probably lost track of the original data anyway, but it's good to not be too locked into just exactly what the output is in R, be able to make sense of output from other programs and software. This is from Stata, which is very popular in social and behavioral sciences and health sciences. So what do we got here? This coefficient is 0.147. And just if you want to write in R, what we would be doing is we would use GLM, or we'd use scan GLM, and basically the same kinds of setup as in LM, except we also want to let it know what family, because this is going to work for a bunch of different kinds of models. And so it's a binomial family, it's a logit. Okay, the bare minimum that people, and often people stop with this, which I heavily recommend against, is to just say, okay, small p-value, equivalently large Z, small standard error compared to the coefficient. So, and this is statistically distinguishable, right? It's non-zero. There is a relationship between newspaper reading habits, the amount of reading newspaper, and the probability of knowing who Pelosi is, but we want to try to interpret it. And in general, the coefficients on logit are not super interpretable. I mean, you can go back, as we did with transformations, and say, okay, well, what does it mean? It means that for every day reading a newspaper, the expected log of the odds of knowing Pelosi increases by 0.147, right? Or the comparison between two people who have a day less or more reading newspaper will have this difference in the log odds, but that's not intuitive at all. But we'll start from the point that, okay, it's positive, right? More newspaper reading corresponds to more higher probability of knowing Pelosi. One way, and this is controversial as to how useful it is, some people think that this is very useful, some people think not, is to go back onto the odds scale. And we've already seen this in transformations. In R, you can take this by just typing out exp, which means take e to the power of what's inside the parentheses, and in parentheses put in, well, you can actually just take the coefficients of whatever your GLM model is, whatever you called your model. So let's say coefficient COEF of, let's say you called your model mod, right? And it will spit out odds. It'll take the log odds and give you back odds. And so in this case, what you would get out would be 1.16-ish, right? Standard error of 0.027. 95% confidence interval, or you can use the MAD-SD if you want to do something more like a credible interval and Bayesian approach, somewhere between odds factor of 1.10 and 1.21. So odds clearly increasing. What does this mean? For every, if you take two people who, one who reads newspaper 6 times a week, one who's 7, or compare one who reads at 0 to one who reads at 1. So any two people who are a day apart in their newspaper reading, the one who reads a day extra has an odds equal to, multiply this factor 1.585, so on, times the odds of the other, right? So increased by a factor of, multiplied by 1.158. Let's say that a little bit more intuitively. Every day per week reading newspaper, odds of correctly identifying Pelosi increase by an estimated factor of 1.15. They go up by 15%. Notice when I wrote this out several years ago, I was not being super careful and really trying to avoid any implications of causation. I don't really mean that, okay, if you intervene by reading the newspaper an extra day a week, you will actually, a single person will have their odds go up. It means that if we take two people, one who reads the newspaper an extra day a week on average more than the other, the one with 1 day more, we'll expect them to have an odds of knowing who Nancy Pelosi is that's 1.1585 times the odds that the other person has. Now, reason that's kind of controversial is that a lot or a little? Well, it may depend on, those odds are going up. It means something different in terms of probability. So we're going to spend time not only going back to the odds, but really going back onto the probability scale and thinking about like, okay, well, so what's the probability that you would know Nancy Pelosi according to this model if you read it 0 times a week, 1 time a week, newspaper twice a week, 3 times a week, because multiplying odds, depending on your starting odds, it makes a big difference. So if your odds were 1 to 100, right? If you are 1 to 99, if you had a 1 in 100 chance of knowing who Pelosi was and recognizing her name, then multiplying those odds times 1.15 would not make much of a difference. But if you already had odds that were like 1 to 1, multiplying by 1.158 would be a big difference. All right, so what about negative coefficients for log odds? Those will correspond to odds as we saw on the scaling before of less than 1, somewhere between 0 and 1. And so, for example, the recognition, the knowledge of who Nancy Pelosi was, at least in the sample, as a function of or conditional on whether the respondent was female, there was a negative relationship. On the odds scale, it's randomly select a female and a male. Whatever the odds are for males knowing who Nancy Pelosi is, multiply it by 0.6075655, so on, somewhere between 0.47 and 0.78 to get the odds that the female will know who Nancy Pelosi is. Far more men that were responding to the survey knew. So multiplying by 0.61 means we would say the odds drop by 39%, right? That 1 minus 0.061. Let's skip that. A couple of others. If I do a lib conservative scale, age, so on, every year and age, odds go up by what? Well, factor of about 1.02 or somewhere between 1.01 and 1.03. They go up by 1 to 3% for every different additional year in age. Education level, clearly. So, normally if we were looking at a regression or looking at the original log odds, we would be looking for an interval that does not include 0 in it. When we're looking at odds, we're looking at a multiple that does not include 1. So either on one side of 1 or the other side of 1. Every year of education corresponds to a difference of or increased odds of recognizing Pelosi that's somewhere between 19 and 38% greater. All else held constant. A couple of other ones. See, here's your liberal conservative scale, where you place yourself on that scale is not predictive in a way that we can distinguish for knowledge of who Nancy Pelosi is. Right, the confidence interval is between 0.93 and 1.10. We don't know whether it's being multiplied as you get more conservative. I think the scale goes larger is more conservative. We don't know whether we're multiplying our odds by a number smaller than 1 or greater than 1, right? Same thing for TV news. TV news, can't distinguish it. You can see the p-values and you can see the confidence intervals that include 1 within them. Again, we would do this in R to get these. You would just take EXP parentheses and the coefficients, either any one of the coefficients you can put in there, and you can get these odds ratios. Being from the South, less likely, right? All else people that have the same amount of newspaper reading, liberal, conservative, so on and so forth, being from the South multiplies by a factor of around 0.65 times the odds of knowing Pelosi if you're not from the South.